Let's talk about interpreting the regression coefficients in a multiple regression and comparing them to each other. Here I've got our Pennsylvania State District data with test scores, 11th grade math test scores, and the percent free lunch in each district, the full-time teacher's salary, student-teacher ratio. So just a reminder, here's the regression we had where we had an intercept term of about 1,300. We had a coefficient of negative 267 on percent free lunch. We had a coefficient of 0.00230 on teacher salary. And we might ask, does this mean that percent free lunch is 267 times as important, actually way more than that, than teacher salary, because this coefficient is much, much bigger than that. But before we go down that line of thinking, we should ask, well, what are the units on these things? So what are the units on the percent free lunch coefficient? It has to produce units of test score points, and that comes when you multiply it by percent free lunch. So the units have to be test score points per percent free lunch. Perhaps as a decimal. That's not super important right now. What are the units on the full-time teacher's average salary? That has to convert dollars to test score points, so the units have to be test score points per dollar. And so these two things are in different units, almost like they're kilograms versus seconds or whatever. And there's just no way to compare 267 of this unit to 0.0023 of that other unit. This coefficient would change if we started expressing things in terms of thousands of dollars or tens of thousands of dollars. The decimal point would move. So with this kind of regression, the regression done just on the data as we have it, there's no way to compare the sizes of the coefficients to get any sense of what's a more important variable. We can look at p-value sometimes, but that's not a good solution for a variety of reasons. So what can we do if we do want to compare the coefficients to get some estimate or some idea of what has a larger effect than another? We would need to make everything unitless, so the units would be the same, unitless, on all of the tests, on all of the regression coefficients. One way to make things unitless is to use z-scores. So let's remind ourselves what a z-score is. It's usually a data value minus the mean for that kind of data value divided by the standard deviation of whatever data value we're talking about, or whatever set of data we're talking about. So here we've got, and those are unitless because whatever units the data value is in, let's say kilometers, you'd be subtracting kilometers, that's still kilometers, and then dividing by the standard deviation of data that's in kilometers, the units are still kilometers, so we'd have kilometers over kilometers, which would be unitless. So that's one reason why z-scores can be useful here, is that they turn things into unitless amounts. So let's show the computation here. So this is saying, look at the school districts tab, school districts 1 in cell E11, subtract school districts tab 1 tab in cell E6, and divide by the school districts 1 tab in cell E7. So let's go look at the school districts 1 tab, and so it's saying, look at this number and subtract the mean for that column, and then divide that by the standard deviation of that column. So we're doing $60,000 minus $48,000 divided by $6,000 roughly, and that gives us a unitless quantity. That's the z-score. And because it's unitless, we should really no longer show these as dollars. We should just show them as generic numbers. We're doing the same thing for percent free lunch. And so that shouldn't be shown in percent anymore. And so we'll convert that to, just show that in those units. We can tell that this is working. It's a good question. It's a good thing to ask, is this working? Here we've got the mean and the standard deviation of the column. We come over to the z-score tab. We're still doing the mean of that column and the standard deviation. And the mean of z-scores for a column should be 0, and the standard deviation should be 1. And so that's working. We should also turn these all into not numbers and not dollars. These are showing now as scientific notation that's very, very close to 0, 10 to the negative 16th. That's just round off error. We don't have to worry about that. So for each of these columns, I'm computing the z-score. I don't really have to do it for this kind of regression that I'm about to do for the y variable, but that will come in handy later, so I'm computing z-scores here as well. So now that we've got everything standardized, so let's write we've standardized the data, made the mean 0 and the standard deviation equal to 1. Some people call it normalizing, but we haven't really changed the shape of the histogram. We haven't made it more normal, more bell curve or anything. So it's, I would hesitate to call it normalized, but some people do call it that. There is another way to make things unitless, which is to subtract the minimum possible value from each data point and then divide that by the range of the data for that column. That gives you results that are between 0 and 1. And sometimes you want to do that, but most statisticians would prefer to do z-scores. So now we're going to do the regression. So we'll load up regression. Our y range is the same as before. And then our x range is, well, let's include the district number here, even though we know it shouldn't really be informative. So we did labels. We'll call this regression z. Never a bad idea to get those. And I suppose I should have changed the column names so it would be clear that I was operating on z-scores here. We could go back and do that later sometime if we want. But let's take a look at these coefficients now. Maybe get them all in the same number of decimals. So that didn't work. There we go. So now they're all roughly the same scale. There we go. They're all taking z-scores and multiplying by things to make a z-score for the overall y variable. So now we can say, oh, percent free lunch does have a regression value, regression coefficient that in absolute value is a fair bit larger than teacher salary, but not massively larger like it was before. But again, we couldn't even really say larger before because the units were different. It's also not a bad idea to say what else has changed or not changed. If we look at the t-statistics and p-values, this is for the z-value regression, and compare them to the original units, we can see that the t-statistics and p-values for everything but the intercept stay pretty much the same. The intercept for the z-value regression or the standardized regression is now, the intercept is now basically 0. That's because we made the mean of all the y values 0. So it didn't need to say, well, the average test score is about 1300. We could also ask what's the r squared and adjusted r squared, how does that change between the two? And that's pretty much the same. So that's because that's a unitless measure and shouldn't change when we change the units of the input variables.